Hi, Dr. Cook here. All right, today we're going to be talking about the modified point mass trajectory model. All right, so modified point mass trajectory, what is that? All right, this is a way to include some of the yaw information so that we get better accuracy without having to follow all of the computations of the full 6 degree of freedom model. All right, this really comes down to being a Goldilocks approach, all right, where we keep the largest factors, the most important things to get accuracy, and neglecting some of the things that have high computation but little input into the accuracy of the model. All right, now we do have assumptions like with any particular model. All right, the first one being that we're dealing with a point mass. So even though we're going to include some yaw information, we're actually calculating this as a point mass. And we're doing that by having a constant yaw that we call the yaw of repose. And we'll talk more about that in a minute. We cannot have high angle. All right, so this works for howitzers. This does not work for mortar fire. All right, it's just the way the model is. There's no rocket thrust involved. All right, we've simplified that out. And we're going to neglect our pitch damping. All right, that's one of the things that we are leaving out of this, and it goes along with having a constant yaw through the whole event. We also are dealing only with rotationally symmetric projectiles. Okay, and these work for small yaw angles. If we have something with super large yaw angles, if it's going to be flying sideways, that's not going to work with this. All right, now as we do this, I'm going to introduce something we call these tilde coefficients. These actually do come in a little bit in the 6 degree freedom model. You can use them also. But really what we're doing is we're starting with that full 6 degree of freedom model, and we're just simplifying how it's written. There's no concept really going here other than algebra. Okay, so we've got something like this variable, the C tilde sub d. All right, so that's a drag coefficient. That's our tilde coefficient of drag. And if we look at that, that's just our drag coefficient multiplied by these other constants. All right, and these are constants, so you know they're not going to change, which means that once we know our coefficient of drag, we can calculate the tilde coefficient of drag with all these other information about our particular scenario. All right, and you'll note that that term is the same one that you see in the 6 degree of freedom model. We can do that for lift. We can do that for Magnus. We can do this for all the different coefficients that we deal with. Okay, so we can look on page 302 to get all of them. I'm not going to put them all here, but essentially they end up being all of the terms from our 6 degree of freedom model, which means we could take that and rewrite it in this fashion. And if you remember the last video, I had to get real small text to make it all fit on the page. But this is, equation 319, but this is the same equation that we saw before, just we've done a substitution. All right, so we've algebraically substituted those larger terms into these tilde coefficients that don't change over the course of our event once we know our particular projectile and its coefficients. Okay. And we can also do that not only for the velocity, but we can do that for our moments with our dH dt. And it really does the same thing there in 9320. All right, so now let's talk about this yaw of repose vector. All right, so the yaw of repose is highly important to what we're doing, to this model. So what is this vector? Well, here's our projectile. Okay, we're going to define a unit vector I that points down the nose, right? So that's a coordinate system fixed to the projectile, but the projectile might not be following that. So here with the velocity vector points in a slightly different direction. That's the tangent of the trajectory, all right? And we've got this yaw angle, alpha t, all right? And that's just how the projectile is flying downrange. Now, if we lay out a vector that is perpendicular to the velocity vector, all right, and comes up to intersect the triangle with our I vector, unit vector that defines our coordinate system, the nose, that is the yaw of repose vector. All right, now an important thing you need to understand is that this is not a force vector. All right, there's nothing physically happening in that direction. Okay, it's just a vector that defines the quantity of the yaw. So instead of using a yaw angle alpha t that's measured in degrees or mils or radians, all right, we have defined a vector that has vector components in our 3 components in 3 space that define how far our nose is pointing, all right, off of the velocity vector, okay? So it doesn't have a force associated with it, all right? It's just a definition to define our angle there, okay? But it is a vector, right? We'll put R as the subscript on that because it's the yaw of repose, all right? So we have a couple different variables that'll come in here. There's a lowercase l vector, all right, which has to do with our velocity vector turned into a unit vector, all right? So our velocity vector divided by the magnitude of the velocity vector, all right? And then we can define our yaw of repose based on that and our I vector, all right, our unit vector of the nose where it's pointing, and that obviously will relate back to our actual angle there, the total yaw angle alpha t, with equation 9.328. All right, so we can do it either way. And we can find out that the magnitude of that yaw vector has to be equal to the sine of the total yaw angle. All right, because we took all this stuff down to unit vectors, that's kind of where we'd end up. Now, once we have that, we can rewrite our 6-degree of freedom model, all right, to make use of our vector for our yaw of repose. All right, and we get equation 9.339 for our velocity equation. Okay, now that understands what the vector yaw of repose is. Now we can talk about specific solutions to these problems. So if we have spinning projectiles, all right, spin stabilized projectiles, gyroscopically stable projectiles, then we're going to have equation 9.378, right, shown here, where we have to take into account what is the spin rate, right? That's the P. We have to understand our moments of inertia around our spin axis, along with the other parameters of our projectile, and some of our magnus is going to come into play there too because we're spinning, right? Now, if we have a non-spinning projectile, we're going to have a different way to calculate out what yaw of repose we will end up at. All right, and you can see that here. We have to take into account some of our magnus coefficients, and we have this gamma term that's brought in here into equation 3.79. So what is that thing? All right, well, that is this L vector crossed with our I vector. All right, and it's equal to the cosine of our total yaw angle alpha t. All right. Now, you'll note that there's some things here. We've got this v, all right, vector. The capital V is without wind. That is the velocity vector that the projectile is moving at relative to our coordinate system, okay? But you'll notice we've also brought in this lowercase v, and that's a velocity when we take into account the wind. So the velocity of the projectile relative to the air that it's moving in, all right, or the medium if we weren't moving in air. This will work for water too. So we have to keep straight. That's why we have the capital V and lowercase v. One is the projectile without wind, and one is the projectile including the wind vector. So to calculate those, the lowercase v is equal to our projectile velocity v, uppercase V, minus our wind velocity. Okay, and that is a minus because we have to keep track of our coordinate system and just kind of which way we've defined as positive about things. All right, so if our x-axis is pointed downrange, with positive being downrange, then a wind that is coming from the tail is going to be the direction that is positive wind. And if we have a headwind that is coming at us, it's going to be wind in the negative direction. So then when we subtract out the negative, we'd be adding it in, all right? Okay, and that brings us to our modified point mass model. Now that we understand how to get this yaw of repose that does not change. Remember, that's our key assumption here, is that we've got a constant yaw. All right, it's based on this yaw of repose. All right, so I'm going to talk here just for spinning projectiles. There are other equations we could get into for non-spinning projectiles when you do that derivation. And this is going to look a lot like our 6 degree of freedom, because we started with 6 degree of freedom and then we dropped some terms out. Okay, so we've got a coefficient of drag coming into play here. All right, dealing with our velocity. We've got a lift portion, a lift term that's coming in here, and we have to understand what our yaw of repose is, because that's what's going to get us into how much lift is coming into play. And then there is some Magnus force that is coming here, so we need the not only the velocity vector, but we have to understand what our yaw is. So our yaw of repose shows up there, and we have spin rate going on because we're dealing with Magnus and spin. And we've got gravity, and we could include Coriolis if we want. All right. Now this version of the equation that I'm showing here on the board comes from McCoy. So that's the equation number if you have the McCoy reference, so you can copy this down if you need it. All right. Now for our spinning, all right, around our different axes. So again, this is a McCoy equation. But yeah, so our rotations here, dp dt, we have lift related terms into that that are going to adjust how much our spin is for our damping on that. All right. Now, we gave some equations for our yaw of repose, but I just want to share with you that McCoy has another version of it, which is based on the gravity vector and the velocity vector and what's our spin rates and our inertia. Now, this is equivalent to what was on the earlier slide with 9.378. All right, if we make a few assumptions. Okay, so in most cases, generally, this is a very practical way to calculate what our yaw of repose will be. And it's just another form of the equation that we can use. Okay, so that's it for the lecture portion of this class. You might have to go back, pause the videos, and copy some things down that you want. But I will see you all in class. Have a great day.